Hey everybody, welcome to a CS302 assignment. So for assignment 1, we're going to be implementing this accordion patience game. And the way it works is you will have essentially a set or a list of stack of cards. And you want to basically move cards from one stack to the other. And the goal is you want to have as minimal amount of stacks possible at the end. So the way it works is a card. So a card from a stack. So you have to look at the top card of the stack. So when you have your set of stacks, the topmost card is only able to move. And you can either move it to the card to the left stack or 3 stacks over to the left. And you only can move it if the top of the card in one stack matches the top of the either adjacent or 3 stacks over. And a match implies either you have the same exact suit, so they're both hearts, or they're both spades, or both clubs, or both diamonds, or they have the same rank, so they're both a 10, or they're both an ace, and so forth. If a card is able to move to the adjacent left neighbor stack, or 3 over, then you always want to give priority to the further over to the left. So if that happens, if you can move the card to the left 1 or 3 to the left, always the precedence always will be 3 over to the left. So of course there's the description of this in this video, or sorry, in this PDF. So that's sort of the idea of this game. So conceptually not too bad, but now of course we're going to introduce, you have to implement various data structures, which of course is going to complicate this a little bit. So let's first go ahead and talk about our custom stack class. Okay, so here is your MyStack class, and let's go ahead and go through the private members first. So this is going to be just dynamic array right here, which is going to be essentially your stack in a way. And then these fields right here essentially tells you, well, the capacity will tell you what's the max amount of elements this array can hold. And then size tells you how much of the array or stack has been used. So the size almost tells you, or it's the index of where the top element currently resides, is the idea. Then we have our clear stack function, is deallocates the stack. Then we have our copy stack function. We pass in a stack object into this function, and it will deep copy this object, or the object that's essentially what called this function, which again I'll discuss. I'll give you some scope on what the this object means if it's a little bit fuzzy. Now, for the public members, our default constructor, as given here in the PDF, it will set the size to 0, capacity to 5, allocates the array of length, capacity, or 5. The copy constructor will do a deep copy of your object. So let me just show you how it's actually used. So here's a test main that you can use for yourself, and this is going to be also used in code grade. So for example, we have a stack object right here. We push a few elements onto our stack, and then, let's see right here, on line 13, here is your copy constructor. So stack 1, that's being passed in, and stack 2, that is going to be your this object, if you will. So stack 2 is what's calling this constructor. So inside this function body, the this stack elements, that refers to stack 2 stack elements, or the this capacity, the this size refers to stack 2's capacity and size. And of course, stack 1, that's going to be the parameter being passed in. So in our description right here, this object copy, that's going to be stack 1, and the stack 2 is understood to be, you don't have to actually pass it in because stack 2 is making the call to this constructor, sorry. Then we have the assignment operator, which is going to be very similar to the copy constructor, and an example of how it's going to be used. Consider this example right here. We have our stack 1, our stack 2, and we have our stack 3, and then check this out. that's calling the default assignment operator. So right here in this object, in this statement of code, we're going to essentially call the assignment operator. And RHS, well, that's going to be stack 1 because stack 1 is being passed as an argument. And stack 3, in this case, that's going to be your this object because stack 3 is making a call to this operator. And then, of course, you want to go ahead and copy everything from stack 1 into stack 3. And you want to do a deep copy, which, of course, you can use the copy stack function to help you out. And, of course, you can call both of those in these two functions. Now we have our destructor. That's going to deallocate our stacks. So you can just call this the clear stack function to make it a bit easier. And the rest of these are pretty straightforward. So the push function is going to push this string on top of your stack. So remember, you want to assign this parameter into the stack elements at index size and then size ++. So then that stack index moves after every single push. And of course, if your stack is maxed out, the push function would have to resize your stack. And so I believe here in a PDF, it tells you to just resize it by doubling the capacity. So double the size of the stack if it does to get maxed out. The peek function returns the stack top, the top element, without removing it. So remember, at index size or size -1, that's going to be where the top element currently resides. So return that element. And then get size returns the size variable, tells you how many elements are currently in the stack. The pop function is similar to peek. It returns that topmost element and also removes it. So when you do a pop function, you want to store the topmost element, decrement your size count by 1, and then return that top element. Then, of course, isEmpty returns true if size is 0, and returns false if size is not 0, I guess, is the idea. Now, it does say here in the description that throw an exception if, let's say, the stack is empty. I'm not really going to check for that in the actual code grade, but again, it's a good idea, I guess. If, let's say, trying to pop an empty stack, maybe throw an exception, so that way the user is aware that something went wrong. So instead of just segfaulting, we get an exception instead, but I'm not going to really focus too much on that. So really, it's a very standard, very basic and simple stack. I would imagine similar one you did in your CS2 class. So let's go ahead and so this is going to be essentially, this stack is going to be used to stack our cards. So we're going to maintain stacks of cards, but we're going to have to use a list of stacks or a linked list of stacks. So I'm going to now go over the linked list class, and then I'm going to try to give you some tips, or maybe give you a little bit of code or some visualization so you can see how the list class and how the linked list structure would need to look like. But let's first just go ahead and just look over the linked list header file just to get an overview before we go into the details of the linked list class. Okay, so here's our giant ll.h linked list class we have to write. So let's go ahead and first just talk about, I guess I'll talk about the first few basic structures. So this linked list is going to be a linked list of stacks. Now, a better implementation would have been is to use templates instead, or use class templates. But really, I'd rather not overdo the first homework too much. So for right now, we're going to just sort of just have it be non-templated. So we have a linked list, and then each element of a linked list will be a struct node. And we have, of course, our element in each node. And then we have a next and previous. So we're going to have a two-directional linked list because, well, it's much more flexible to have a two-directional linked list. And in reality, in terms of programming, power, computing power, it's not more complex of a structure. It may be more thinking for you, the programmer, but in reality, it's not so over the top in terms of, for the machine, it's not an overhead really to maintain these two pointers. So we're going to have a two-directional linked list. And now to make things even worse, it's going to be a two-directional linked list with a dummy node. And it's going to be, with this dummy node, it's going to be a circular linked list. So notice, for our linked list, for our private members, we have our node. And then we have our two private functions, which can be used for our destructors and deep copying. And then we have this node star dummy. There is no head and tail. And we're not going to need it because this dummy node that will enable this circular sort of direction or circular path, that's going to allow us to access the head and tail nodes through this dummy node. And this, I will definitely draw the example here in a little bit to give you an idea to help you visualize what I mean by this. Let's go ahead and just first discuss the Iterator class. And then this is very bizarre how we have our class linked list. Here's our private members. Now here's our public members next, but check it out. We have an Iterator class defined within our linked list. And the reason why I do this is because, well, it makes sense because an iterator without a linked list, there's no purpose. It can't really live by itself. It really needs a linked list, essentially. So it makes sense to just kind of define this class within our linked list. Now, luckily, for the implementation files, I will give you all the function headings. You have to fill in each blank. So don't worry about all the crazy syntax that will come up with this. So for right now, let's focus on this iterator. And first of all, let's focus on trying to understand what this actually is and why do we even need this. So the iterator is going to really behave like a pointer, where it's going to allow us to iterate or navigate through a linked list like a regular pointer. So then the question is, okay, well then why do we have an iterator? Why can't we use a pointer instead? And the answer is, well, it's for this encapsulation topic, remember from CS 202 for object-oriented analysis and design, you want to enable encapsulation. So we don't want to have pointers really being defined in our main, because it could cause all kinds of chaos in our program. So the iterator is going to be an abstraction which will not expose that pointer, but it will still give us a flexibility to traverse the linked list as if we had a pointer. So for the class iterator, all of the actual function code will be given to you. So these functions right here, I actually wrote these for you in the ll.cpp file, but some of these I actually kind of inlined them because they're very basic. So let's go ahead and look at this iterator class really quickly. So this friend class ll, all this really means is that if we define iterator within our linked list class, we are able to access the iterator's private member. Now right here for the class iterator, we only have one private member, node star position. So that's where we actually sort of encapsulate that private pointer member. So an iterator contains a reference or a pointer to a node in a linked list, but notice that we keep it private so we don't allow in main to access this pointer directly. So now we have our constructors, very basic. Our default constructor sets our pointer to null. This constructor, we assign this pointer to position. Now, the star operator is kind of a dereference, except that we're not dereferencing a pointer, dereferencing an iterator. So what the star operator does, it returns the, so it's essentially each iterator points to a node in a linked list. The star operator is going to return the linked list's item field. An item is a stack object, so it's going to return the stack object contained within a node that an iterator points to. And I'll show examples so you can see how this looks. Then, of course, we have our comparisons to determine between two iterators if they point to the same node or not. So the equals equals operator is true if two iterators point to the same node, and false otherwise. Not equals is the opposite. Now we have our plus plus and minus minus. So I believe this one is going to be a postfix plus plus. This one's going to be a prefix plus plus, which means that we can have the plus plus operator appear before or after the iterator. And what plus plus does it will simply move the iterator over to the right, and minus minus is going to move iterator to the left. And again, these two functions will be given to you, but that's what the plus plus minus minus actually do. So let's go ahead and look at the rest of our linked list class for a second. So the rest is kind of more or less, I would think, kind of a review from CS2. So we first have our default constructors. Let me just move like this. So we have our regular default constructor. This constructor is going to basically essentially allocate a dummy node and then set dummy nodes next and previous, either both to point to null or to point to themselves. It's up to you how you want to set this up. And again, I will draw this out so you can kind of visualize how this works. Then here's our copy constructor. So we have to deep copy our linked list. Here's our assignment operator and destructor. So let's just quickly go over what these actually do. So here we are. So right here, we create a few stack objects, and I'm going to have a linked list object list 1, and I, insert some elements into my linked list. And same thing, this is going to be my copy constructor. So I'm simply going to have to deep copy every node from list 1 into list 2. List 1 is going to be the parameter. List 2 is going to be this linked list object. And same idea right here. We can deep copy from one list to the other using the assignment operator. So in this context, if we look at the operator equals right here in our PDF, list 2 is going to be RHS, and then list 3 is going to be this object. So that's kind of how they're going to be called. So we're going to test these out. So on code grade, I'm going to have it compile or link this main to your linked list implementation file, and it will test these out to make sure you correctly implemented the deep copy constructor and the assignment operator. Destructor deallocates your linked list. So again, you can use the clear list and copy list functions accordingly to help you implement the default constructor, the assignment operator, and the destructor. Head insert inserts a stack object to the front of our linked list. So we essentially allocate a node to the front. We do a head insert, and then we assign that node's item field with this parameter right there. Tail insert, same idea, except we do it to the end of the linked list. Head remove does a head remove, so it removes the first node of the linked list. Tail remove removes the last node of the linked list. Now this function, remove at position, we pass in an iterator by reference, and this iterator is going to point to a node. This function is going to deallocate the node that this iterator points to. And after the function terminates, we want to make sure this iterator is going to be now assigned to the next node afterwards. So essentially, if you deallocate a node, an iterator points to that node, it deallocates it, but we don't want to leave that pointer or that iterator dangling, so we make sure we set it to the node that would have came after the node we just deallocated. Then is empty, returns true if a linked list is empty, false if it's not. Now these two functions, I also give these to you as well, begin and end. Those are mostly for iterators, so we can set the iterator start at the front of our linked list and then move from left to right, or we can have our iterator point to the last node of the linked list, our tail node, and move from right to left. So begin and end essentially return an iterator whose position points either to the front node or to the tail node. So let me go ahead and see if I can look at these main files and then kind of show you a little bit of how these plus plus minus minuses work. And of course, I will soon actually draw a linked list example and help you kind of visualize how it would look like, and it will help you potentially code this. So basically, this is kind of straightforward. Let me see. Okay. So let me just take a look at maybe this example. Here we are. So here's an iterator object we defined. So in this case right here, we have a linked list. We put some elements onto it, tail insert, and so forth. And here's an example of an iterator.
So when I say it equals list.begin, it's going to set the iterator to point to the head node of the linked list. And then while it's not equal to the end, we're going to do it++, which is going to essentially move the iterator one node to the right, one at a time. So that's how the plus is to be used. And same thing, we can check this out in our linked list removals file. So over here, same idea. We can have iterator it. It can be assigned. So list.begin is going to assign it to point to the first node. And then we can do plus plus, minus minus, like this. So the plus plus simply just moves the iterator to the node adjacent to the right. And then, of course, we can essentially assign, or minus minus will just simply move the iterator to the adjacent node to the left neighbor. And that's basically about really the idea. But I will kind of maybe also give you a visual for iterators as well. So now I'm going to talk about more of the visual details so you can kind of see how the linked list class is to look like and how iterators look like as well, to give you some scope on this. And that should be that I might talk a little bit about the main accordion a little bit at the end. Let's go ahead now, just go over our visual for a linked list. Okay, so here's kind of a visual for how the linked list structure will look like. So each of these nodes, well, they're just nodes, so it's a struct node, and each node has 3 fields. So this middle field for any node, the middle field will be the item, which is going to be a stack object for our linked list. This is going to be the pointer, the previous pointer, which contains the address of the left adjacent neighbor. And this subfield right here is going to be your next field, which is going to be an address or pointer to the right adjacent neighbor. And here's your dummy node at the very end. This dummy node will contain nothing useful. It's really going to be almost like a bridge that connects between the head and tail. So in this arrangement of our linked list, this node right here would be your head node, and this node right here would be your tail node. And notice the tail node's next points to dummy. The dummy node's previous points to the tail. The head node's previous points to dummy. And dummy's next points to the head. So this dummy node right here is your bridge. Because if you hit your tail node, if you go beyond the tail, then you wrap around back to the front. If you're at the front and you go to the previous, you wrap around back to the end. So whenever we call the begin and end function for iterators, the begin returns the address of this node, and then the end actually returns the dummy node, not the actual tail node. So let's go ahead and just quickly go over just a visual for how the iterator would look. So if I define an iterator, so it would be LL, iterator IT. Now, because iterator is defined within the linked list class, we do need to have the LL followed by a scope operator, and then iterator is our custom type, but it exists within the linked list class. And there's IT right there, so we can almost visualize it as, here's your IT object, it's iterator object, and inside of it, it has that node star, what was it? I think it was current or position, but it contains that node star field within it. Now, if I say, let's say, for example, this object is just called list. Let's suppose I have a list object. Then we would have, you could do it equals list dot begin. And the begin function is written for you, so don't worry about it. What this is going to do is going to set the iterator's current to point to the first node of your linked list, which is, maybe I'll draw this arrow a little nicer actually. It'll point to this node. And then, of course, if I were to say, star IT, it's going to retrieve that item, that data field of that node. In this case, star IT is going to return a stack object because our linked list is going to be specifically used where each node contains a stack or a MyStack object. So it's going to return that stack object to us. Now, if I do IT++, it will simply move this pointer. Oops. It'll move this pointer over to the next node of the linked list. Or if I do ++it, it will also work because we implemented both the prefix and postfix operators, and it will then move over to the next node. That's basically it. So the iterator class, all it can really do is be set to the begin or to the end, and of course you can do ++ or - to move the iterator around. So it's going to behave really just like a pointer, except it's in iterator instead. That's all. Now, if I wanted to actually set the iterator to point to the tail node, the tail node would be this node right there. What I'd have to do is I have to set the iterator object to the end. However, if I do something like this, if I were to say it equals list.end, the problem is it's going to set this iterator to point to the dummy node because the end iterator returns a dummy node, which we don't want this. So what we'd have to actually do, a simple workaround would be just to say - list.end. So list.end returns that dummy node, and then - sort of moves over to the left by 1. So in other words, it will set the iterator to point to your tail node. And then of course we can do, it - or -it. But remember, the - operator is implemented to simply move the iterator over to the node to the left. And that's basically it. So you can also write a loop that can iterate through a linked list. So there's really two ways to do this. You could either go from left to right. So you can say for it equals list.begin. And then you want to do it not equal to list.end. So list.end is almost like our null pointer, it++. So once it hits the dummy node, we're done. We went beyond the bounds because that end iterator or the dummy node is kind of, we fell off the list basically. So that means we went beyond the list. So once we hit that dummy node, we're done. This will iterate through our linked list from left to right. If you want to go from right to left, then you would just have a for loop. Just set it equal to list.end, which is going to set this iterator to the tail node. And then we're going to do while it is not equal to, once again, list.end and it -. Now, even though you would think this is the end iterator, in reality, this means you fell beyond the bounds. So if we set it to be the tail node, like using this code right there, it would point to this node. We do it -, it would just keep hopping in this leftward direction. And then when it hits the front node, we go to the left once again, we go back to dummy, which means that now the iterator it would equal the end, or it would equal this dummy node, so it will stop looping. So if you go to the left of the head node, or the right of the tail node, in both cases, we hit that end iterator, or that dummy node. So that's kind of how we would navigate through a linked list. So that's kind of our visual for how our linked list can be interpreted. So now I'm going to go ahead and give you a little bit of help to get you started with some of the coding. So we're going to sort of begin this using an empty linked list. And then from there, we will kind of show you, or I will show you a little bit as to how you would just be able to maybe insert a node into the linked list, and just so you can kind of try to refresh this pointer code. So let's go ahead and get to it. Okay, so here's how you can visualize your linked list when you declare your object like this. So you have a dummy node, and you want to set it equal to a node. And then you have the option of either having this dummy node's previous and next both point to themselves to kind of form, I guess, a heart. Or it looks like maybe sort of two bros just kind of giving each other a high five. Looks like that. I just saw that for a second. But anyway, you can do that, or you can have it where you can just set these two to just both be null, the next and previous. It's really up to you as long as you're consistent. So when you do your isEmpty function, you make sure you're consistent that if your dummy nodes next and previous either both point to null or they both point to itself, that would imply you have an empty linked list. So maybe having them both be null is probably actually easier to work with. So you would first, in your constructor, allocate a node. So dummy equals new node, and then dummy arrow next equals null pointer, dummy arrow previous equals null pointer. And then there you are. Okay, so suppose I want to insert. So I will, for now, just maybe I'll do a tail insert. And I guess you would have to put like a stack object right here. So I would just maybe just say my stack object. Since we are working with a linked list of stacks, and since our linked list is not a class template, we'll have to be consistent. So imagine somewhere I defined an object of type MyStack. So we have a MyStack object right here, and we insert this into our linked list. So what we're going to do is in our function body, so I guess I can give a little bit of help here. So in our function body, we may want to first check if our list is empty or not empty. There's really two cases to consider. So if it's empty list, we have to do slightly different code. But either way, we want to have a node star. And I'll just call this, for now, maybe I'll create a temporary variable called tail. So I'm going to go ahead and just write this tail pointer right here. So we first need to set tail equal to a new node. Remember this from CS202. We just do that. And we have our node right there. And then tail is going to point to this node. Fantastic. Then I will set tail, I believe it's called item, equal, well, I'm going to set equal to the parameter. So whatever the parameter I pass in, I'm going to assign that right here. So I'll use X for right now. But you assign something, so you want to put a stack object into that field of our linked list. Okay, so that part is now good. We have to now properly link this up. So right now, with our linked list being empty, the issue is this node, at the end of the day, is going to be your head and tail node. Because remember, from CS2, if you have one node in your linked list, that node is going to be your head and tail node. So you have to kind of link this up the right way. So for one, I'm going to go ahead and just say tail arrow next equals to dummy. Now, one thing to consider, be careful with these statements. So, for example, tail equals or tail arrow next equal, they are kind of similar, but they are very different from each other. If I say tail equals something, then we're going to reassign this tail point to the point somewhere else. If I say tail arrow next, remember what that does? That's going to basically dereference this pointer, and it's going to reference the pointer, and it's going to access the next field of that node that tail points to. And we're going to assign that next field to point to the node that dummy points to. So in other words, it's going to just do this. Then of course, you want to set dummy arrow previous equal to tail. So again, we're saying dummy arrow prev, which means dummy arrow means I want to follow that arrow, access that object, that node that dummy points to, and I want to access that prev field of this object, which is right here. And I'm going to assign this to point to the same node that tail points to. So it's a shallow copy, but we want this because we want this node's previous to point to this newly inserted node, and we want this newly inserted node's next to point here. Now, since it's going to be both our front and back node at the same time, I have to make sure that the dummy next points to this node and this tail's previous points back to dummy. So to do this, well, just do tail arrow previous equal dummy. So the previous will point back. And then, of course, dummy arrow next equals the tail, which will just take the dummy node's next field, and it's going to point it to this node. So now, essentially, we have this bridge set up where the end node points to dummy. Dummy's next points to the front. And this front node, so basically because we inserted into empty linked list, this newly inserted node is going to be both the head and tail node. Now it's all wired up correctly. Now, a lot of times students want to say, okay, well, I'm going to go ahead and delete tail now because I don't want tail to point to this node. Remember, delete is a very bad word in C++. It doesn't actually delete anything. It's going to deallocate this node. Essentially, it will undo everything in one step. So you don't want to say delete tail. If you want to clear the address of tail, you don't want this pointer to point to this node anymore, you could say, this is optional, but you could say tail equals to null pointer. And that's going to clear this pointer, so now tail will point to nothing, if you wanted to. Now, it's optional because once you escape this function tail insert, notice how we defined this node star tail locally inside a tail insert scope. Once this function terminates, this local variable is destroyed, only dummy remains, because dummy is an instance variable of your LL class. As long as the object exists, dummy will also exist. But tail only exists inside the tail insert function body. So really, when the function terminates, tail will be destroyed, and then you don't have to worry about anything, really. And that's it. So this actually works for this is actually an edge case where if you have an empty linked list. So now you have to essentially worry about tail insert for a non-empty linked list. Let's go ahead and quickly just create an example of more than one node and see how our tail insert works in that particular instance. Okay, so let's consider a case like this where we have a linked list with many nodes. So I want to do a tail insert. Well, right here, this is my current tail node right there. And this is my dummy, so I want to insert something between these two nodes because I want the new node to be my new tail node, so it has to kind of scoot between my old tail node and this dummy node. So it's going to be a similar idea. So we're going to create a few pointers. So I'm going to first create a pointer called tail, and I'm going to create maybe a pointer called old tail, just so it's going to be helpful to have multiple variables for this problem. So I'm going to first set the old tail equal to dummy arrow previous or prev. So what's going to happen is old tail will point right there because remember the rule is that dummy node's previous always points to the tail node. This is my current tail node right now. So now I have to allocate a new node. And to do this, well, I just say tail equals new node. So I'm going to just maybe create tail right here. And I'm going to go ahead and just copy this. Okay. So I'm going to go ahead and put this node right there. And then tail points to it. This is my newly created tail node. So once again, well, we're going to set tail arrow item going to equal to x. It's going to essentially equal that parameter that when we call the tail insert function, we pass in some stack object, and that parameter will be assigned to this node's item field. So we first just take care of this. So now we have to essentially assign this node into the tail node's position, which means that essentially this has to be right before the dummy node. So what we do now is we say dummy arrow previous equals to tail. So right now dummy points to the old tail. It'll get reassigned to that node. And then I will say tail next equals to dummy. So these two are now connected. And now what we have to do is make sure it's linked up to our current linked list. So what's going to happen is, since this node is my new tail node, the old tail has to point to it, and this tail has to point back to the old tail. So to do this, what I would do now is I would just say old tail arrow next equals tail. So remember, once again, old tail arrow means we're going to dereference this pointer, access the next field of the node that old tail points to, and I'm going to reassign that next field to be assigned to the same node that tail points to. And then what I'll do is I will just set tail arrow previous, have it point to the old tail. The same idea. Tail arrow pref or previous means I want to access the previous field, because the arrow operator here means dereference. So I want to access the node, and then I want to pick the previous field. I'm going to assign that previous field to point to the same node that old tail pointer points to, which is that node right there. And now if you were to imagine, if I grab this node and the dummy and just sort of pulled, this tail would just be sort of inserted between old tail and dummy. And that's it. We did our tail insert. So really, it's a very step-by-step data structure. We have to basically just one by one allocate the node and just reassign these next and previouses accordingly to essentially fit a node into the correct spot. So think of these as little blocks, and these are like strings trying to connect them to each other. So if you're doing a head insert, it's going to be fairly similar to tail insert, except done on the front end of the list. So if you do a head insert, then we have to essentially connect these two nodes together and make sure the new head nodes, previous and dummy, are linked. So I'm not going to give you that. I'll give you the idea, but it's very similar to this. And again, I won't cover every aspect of the code for this. This is kind of a review from CS2, but I wanted to give you at least a little bit of code, a little bit of an idea, so to help you get started if in case it's been a while since you've done C++. So again, most of the linked list contents, the code is fairly similar to CS2, except it's doubly linked list and we have this dummy pointer, but it's not so much different. An iterator, that's only going to be used really just in the main program. Inside your linked list class, in the actual linked list class functions, you can just create pointers, node star. The iterator is mostly needed really in main because we want to encapsulate that private pointer. But if we're in the class linked list, then there's really no reason to have an iterator at all. So anyway, that's sort of just kind of a little review, and of course now you have to write the rest of the functions, and I have several test mains that are going to test out different functions of your linked list class. So now I'm going to go ahead and maybe give a little bit of an idea for this accordion game you're going to have to write for your main. Okay, so here's a given situation where we have this linked list, and each item field in each node is going to be a stack object, and then these are going to be the elements on our stack. So we have 8 of hearts on top, and then we have ace of spades. This array, or this element, this stack has 2 of spades, jack of hearts, and so forth. this pile, this stack only has one card, just the 8 of spades, and so forth. So we have an iterator that points to this node, and basically we want to be able to check the top of this stack. So to do this, we can just do star it. That returns the stack object contained inside the node, because remember, this star operator will dereference this iterator, which will access the item field of that node. And then we can do a dot peek function, which will then return to us the top card of this stack. So in this case, it's going to return back to us the 8 of spades. Now, when we're on a certain, looking at one of our stacks, we want to compare the top card of, let's say, IT to its left adjacent neighbor or 3 neighbors down. So we want to create additional iterators. Now, to do this, you'd have to, of course, set j equal to it, I equal to it, and do I minus minus, and then do j minus minus a couple of times to get this scenario. And now you can see here that this 8 of spades is actually able to go onto this pile or this stack, and also this one, because the adjacent neighbor doesn't have the same card rank, but the same suit. And then 3 sort of stacks down, this topmost card has the same rank. So when this happens, we want to, of course, give priority to the one that's 3 sort of neighbors down. So you have to, of course, pop the stack right here to retrieve this 8 of spades, and then we have to push it onto this stack. So we could do, star it.pop, star j.push. We have to take this and push this over here. Now, when this happens, and there are certain cases where when you pop this and push it somewhere else, this stack becomes empty. If that's the case, we have to deallocate this node by calling the linked list remove function, pass an it. It would deallocate this node. It would set it over to the next neighbor. Now, when we move a card, let's say in this case we moved 8 of spades over, we want to see if we can move it any further down. So there could be more stacks of cards, but I only focused on this portion right here. But after we move 8 of spades down to this stack, we want to see if we can move this topmost card possibly further to the left. So you want to move it as far to the left as possible. And then once we're done, then we pick another card. We pick a card in our stack, and then we try to move that down as far as left as possible. And again, when this happens, we essentially remove one of our stacks. And the goal is you want to move cards around such that we want to minimize the amount of possible stacks we can have. So this is actually an old ACM competitive coding problem. So I'm not going to give away the entire technique, but there are different ways to attack this problem. So you could move from left to right or right to left, and you want to look at a stack. So IT points to a stack. Then you want to create 2 iterators, one that points to the immediate left, one that points to 3 neighbors down, and then see if the top card in IT matches a top card with rank or suit to the adjacent left or 3 neighbors down. If 3 neighbors down matches, we pop, push it there, and then we try to see if we can move it any further over to the left, if possible. And then we try the same thing again on a different card in our stack. So this requires a little bit of having some loops set up here, but that's sort of the idea. So then after you do this, maybe you can then move on to the next element, Queen of Diamonds, and see if this can move over. If it can't, try the next card, and so forth. So you may have a couple of levels of nested loopings. You have to have one loop that kind of iterates through your stacks, and then one loop that tries to move the top card over as far as possible to the left, and we deallocate nodes along the way if at some point we end up getting an empty stack, and we just keep doing this over and over again until no more cards can move, and then we're done. And hopefully after that, we minimized our amount of stacks. If it's not minimized, then perhaps you chose the wrong stacks to move when you first began this algorithm. So I'm not going to give it away, but you have to either go from left to right or right to left. When you're picking a card to move either to the left or 3 neighbors down to the left, which card you choose, the order in which you choose is going to actually matter. So you want to be careful as to what order you choose. So that I will not give away. That's kind of, you get to have the fun and the joys of doing that. So let me go ahead and show you a test run of this program, and then that'll be at the end of the video. Okay, so let me go ahead and using my Linux terminal, let's go ahead and just first show the input files we're given. So the first file is going to be cards01.txt, and here are the list of the cards. So basically, it's going to be an array of strings, and we have basically each string has 2 characters. The first character will be the face or rank of the card. Second will be the suit. And then for 10, we'll just use the actual letter T for 10. So we have essentially 2 up to 9, then T, J for Jack, Queen, King, and then A for Ace. So 52 cards right here. So what you want to do is read from this file. You want to create 52 piles or stacks. Each has only 1 card in it. I would say start with that first. And then from there, you want to determine how do you choose, where do you start this accordion? Where do you begin to move cards to the left? Where do you start from, the leftmost or the rightmost? One of those will give you the more optimal solution, or it will match the solution on code grade. Now, we're going to use Linux redirection to read in this file. So you have to use cin to read the file, but you're going to use the end of file control loop with cin. So here's how you would compile this. So we have to do G++, and we have to compile mystack.cpp because we're going to create a linked list of stacks, then ll.cpp, then of course whatever main you're working with. Now it's compiled. Now to run this, of course, /a.out, and I'm going to use that symbol right there, which is going to be our input redirection, and then cards01.txt. So whenever you use cin in C++, it always reads from a default standard input or reads from the console. But right here, I'm directing it so cin is going to actually read from this file. So cin is going to really behave exactly just like an input file stream variable. So this way, this is definitely kind of an easier for code grade, so we can just feed in input files and not have to open up file streams and so forth. It's a bit of an easier trick. So just use cin, treat cin like really a input file stream variable. So you do while cin.eof or not cin.eof and so forth. And of course, here's our answers. We have 6 stacks, and basically we just have to essentially output each stack. There's 6 of them, and then we give the topmost card and then the actual size, how many elements there are in that stack. So we have 1 stack, the leftmost has a 2 of hearts on top with 40 cards. Next one has Queen of clubs on top, 8 cards, and so forth. Then for our other file we're given, this creates only one. It's 1 stack, not 1 stacks, but I'd rather just not worry about the logic there. So there's 1 stack, and 52 cards are all in 1 stack, and topmost card is a king of spades. So essentially, you just read in your file like input file stream variables, but you're going to use, this is going to allow you, these will allow you to essentially read in your file using cin. I would just say read in a card 1 by 1, push it into a stack, and then tail insert that into a linked list. And then I would say read my next card. So let's say for cards 01, for example, we read Queen of Diamonds first, push it onto an empty stack, and then tail insert that stack with Queen of Diamonds onto your first linked list, first node, sorry. Then read your next card, Ace of Diamonds, you push it into an empty stack, and then you tail insert that into your linked list. So then you're going to have 52 stacks, each having 1 card, and then you have to now
start to implement this game. So it's not anything extremely complicated, but again, you want to be careful with the edge cases because you want to make sure that if you, let's say you're at the first, second, third node, you want to make sure you don't go beyond the bounds of your linked list as you start moving cards around and so forth. So anyway, so that's essentially the video. So hopefully this gave you some ideas to begin. So I guess that's it. So I guess happy coding and till next time.